Alright, what we're going to do in this video is look at how we can calculate statistical power for a procedure knowing something about the population after treatment. Now all of this requires that we can predict reasonably what the mean after treatment would actually be for a population. So starting with the example we've seen before, if we could actually predict what that population mean after treatment is, we would be able to determine the power of our procedure to detect it. And remember, power is just the likelihood that we would actually get a statistically significant result if the alternative is true. That is, if there is a real effect in the population. So to start this off, we have to talk about first the distribution of our test statistic if the null hypothesis is true. So this is if there really is no effect. And the reason we start here is this is where all hypothesis testing starts, this distribution of the test statistic if we believe the null is true. So for that particular circumstance with Facebook, if the null hypothesis is true, the mean after treatment is 15. That is, the samples we would get would tend to be around 15. Sometimes they would be further up, sometimes lower down, but that's what our sample mean would be trying to approximate. Now what we do in hypothesis testing is we try to decide between whether sampling error is a reasonable explanation for an effect we see, or whether we think there really is some effect out there, that is, our treatment has an effect. And we set this up with these extreme regions representing places where if we get a sample there, we don't reasonably think sampling error could have caused it. Now if the null is true, of course we get samples all over the place, and some of the time, specifically a proportion of the time equal to alpha, we're going to get samples that are in those extreme tails, just by chance alone. Just because we get a sample up there doesn't mean that the null hypothesis is false. It just means that we got a sample that was very unlikely if the null hypothesis was true. Alright, but now what we have to talk about is the distribution of our test statistic if the alternative hypothesis is true, if there really is some effect in the population. And in this example, or when calculating power, you always do have to assume there is some effect. Because you can't talk about power if there's no effect out there. There's no way to make a correct rejection of the null hypothesis if the correct decision should have been to retain it. So we're going to pretend that the mean after treatment was 16 hours exactly. That is, after treating the whole population, the mean of that population was now 16 hours. Now we can see this is a real effect. The null hypothesis is false. Of course it's false, because the population mean after treatment is not 15. So what we're going to do is talk about the distribution of our test statistic if the mean after treatment really were 16. That is, we're taking a sample from that population, we're pretending we are anyway, a treated population, where the mean is actually 16. Now what I want to do here is have a distribution that shows what types of z sub x bars, what types of samples really, I'm likely to get if the mean after treatment really is 16. Now we can locate this distribution. We actually already did the z-score calculation for a sample mean located at 16. But what we want to do is talk about a population mean centered at 16. Now I can use all these calculations but change the symbols. And the reason I'm adding these subscripts is that when you do these problems, you have a number of things to keep straight. You have the mean if the alternative is true in a particular way, you have the mean if the null is true, and you have the standard error. So what I've done is just added subscripts so we can be really accurate about what we're trying to find. What we're trying to find is the z-score for a population mean if the alternative is true, and we take the mean of that alternative distribution, which we have to pick. Of course, we're calculating power for a particular situation. We take that mean minus the population mean if the null is true, divided by the standard error. And notice this gives us again 2 as our z sub mu alt, the same z-score we had for our sample mean that was at 16. And that just sort of makes sense. All we're trying to say is in a sampling distribution relative to the null hypothesis, how far away is a mean of 16? Whether it's a population mean or a sample mean doesn't really matter. But I'm adding the subscript so we can keep straight what we're actually calculating. So I can draw in this distribution now, the distribution of our test statistic if the alternative hypothesis is true, with a mean of 16 after treatment. a particular true alternative hypothesis. And that's what the blue distribution is there. It's true that if the mean after treatment was 16, this distribution would be centered right at 16. Right? That's what it means to say the mean after treatment is 16. And this distribution represents all the samples we could get from that population. Remember, we're not always going to get a sample mean at 16. Just like we would never expect if the population was centered at 15 that all of our samples would be 15, we have sampling error. Sampling error is always happening. So even if the mean after treatment is 16, sometimes our sample means are going to be above that blue bar, and sometimes they're going to be below. And we know it's going to be symmetric because we know a lot about how sampling distributions work. But that's the distribution of our test statistic if the alternative is true in this particular way. All right, so now that we have that, we can actually shade a region of this distribution which leads us to make a particular decision. That is, we have the critical value of z right down there. It's 1.96. Now, anytime we get a sample with a z-score above 1.96, that would lead us to reject the null hypothesis, because those are the sample means that couldn't be reasonably accounted for by chance. Those are the sample means where we would say sampling error alone is not a good enough explanation. Right? So if I shade the proportion of this blue distribution beyond 1.96 standard errors relative to the first distribution, the distribution of the test statistic under the null, what we get there is power. Right? This is the proportion of the time we would get samples z sub x bars if the alternative is true in that particular way, if mu treatment is 16. Because notice, if we get a sample mean, or a sample z-score, z sub x bar, above 1.96, that will lead us to reject the chance explanation. It'll lead us to reject the null. What we've drawn with the blue curve are all the samples that we expect to get if that distribution is centered at 16. So it makes sense that the proportion of that distribution that's above 1.96 is just power. It's the proportion of the time, if the alternative is true in this particular way, that we're going to get a statistically significant result. If you imagine we have 100 researchers doing this exact same experiment, some of those researchers will get sample means that are in the blue shaded region, and some of them are going to get sample means that aren't. Because remember, not everybody's going to get a sample mean exactly at 16. Sampling error is always acting. Sometimes researchers will get a mean of 17 or 18. Sometimes they're going to get a mean of 15, right? Even though that population is centered at 16, sample means are going to vary around it. Some of those sample means will exceed the criterion that is necessary to reject chance as an explanation. But for some people, for some of the researchers, they're going to get sample means that look as though sampling error could be reasonably the cause. That is, these samples down here, the ones that aren't shaded, right? Those are sample means that we actually set up in a situation could be reasonably attributable to chance. Of course, think about it this way. There's some of the time, even though we're taking samples from a population centered at 16, some of the time we're going to get a sample mean that's exactly 15. That's the mean before treatment. Of course, that sample mean is going to look as though it's reasonably caused by chance. It's exactly at the population mean before treatment. Some researchers are just going to get unlucky, and they're going to get sample means that are way down there. Similarly, some researchers are going to get sample means that are way up here, that are going to overstate the effect. The point here is that there's some proportion of this distribution that's beyond 1.96. That's beyond the cutoff point before we can reject chance as an explanation. All right, so what we're trying to do here is calculate this proportion. So the first thing we need to do, and it will make sense why we do this in a second, is find the critical value, that is that 1.96, but in the original X units, in the units of hours on Facebook. So what we're looking for is this value, the one that corresponds to 1.96 standard errors, right, relative to the null distribution, that z-score of 1.96. Now it should make sense, we're going to use that z-score to X formula, but I've changed it around a little bit with subscripts to make sure we know what we're finding. Again, what we're looking for is the critical sample mean. The sample mean that if we get one above it would lead us to reject the null hypothesis. This is just like a critical z-score. It's just now the critical z-score in terms of sample means. So x bar critical is just equal to the mean under the null hypothesis plus the critical z-score times the standard error. This is exactly the same as what we've done before. X is equal to mu plus z times sigma, except now sigma represents something very specific, the standard error. The z-score we're using is the critical z, and mu is the mean under the null hypothesis. So if we add in these values, that's 15 plus 1.96 times a half, or 15.98. That's that value right there. It's the value that corresponds exactly to 1.96. And this is the critical mean. We could do a hypothesis test using this value. We could find this, 15.98, before we did the experiment. That would be our critical mean. And then if we get a sample mean above 15.98, we could reject the null. This is exactly the same as doing the experiment and then z-scoring our sample mean and comparing it to 1.96. It's just when do you want to do the z-scoring. You could do it beforehand and get a 15.98 as your sample mean that's critical, or you can get your sample mean and then convert it to z and compare it to your critical z value. Identical things. So all we've done is found what 1.96 is in terms of x. Now the reason we're doing this is because once we've found this value, we can actually forget completely about the distribution of the test statistic if the null hypothesis is true. That is, we can completely forget about it, because now it's actually totally unnecessary. What we're really trying to do is to find the proportion of this distribution, just this single distribution, that's beyond 15.98. That's all we have to do. So in fact, in step 3, I'm going to ask you to forget that you're doing anything complicated. At this point, you're really not. We had to do some complicated things to get here, to set up the problem. And it's sort of a complicated idea to think about. It's a little more abstract than some of the other things we've done. But at this point, you can forget completely that you're doing anything complicated. We can actually get rid of all that extra information and just phrase this problem like the z problems we've seen before the midterm. Specifically, we can just say, what's the proportion of this distribution greater than 15.98? Doesn't matter that we're representing sample means. We just want to say, what's the proportion of x greater than 15.98? So before we go on, I think it's helpful to come up with a guess here. The mean of this distribution is 16. We're looking for the proportion greater than 15.98. Should that proportion be greater than 0.5 or less than 0.5? Take a second to think about that. Now hopefully you came up with A. That proportion should be greater than 0.5. Because if you think about it, we know there's half of this distribution greater than 16. And I'm asking you for the amount greater than something a little bit below the mean, 15.98. So that proportion has to be greater than 0.5. So when we look up a value in the z table, which is what we're going to do, remember that we're looking for something greater than 0.5. So now all we have is a standard z problem. We're going to find area under the normal curve using what we've done before the midterm. We sketched the distribution, which is already done. We've shaded in the area to be found, also already done. We're restating the problems in terms of z. We have to do that, and then once we do that, we can use the proportions of the unit normal table to find the area. So if we go back to this problem, what we want to do is state it in terms of z, what proportion of a unit normal distribution is greater than that value. So to do that, we're going to use our x to z transformation. I'm going to add in some subscripts again to make sure we remember exactly what we're doing. Now, I've already told you to forget that we're doing anything complicated, but keeping these subscripts actually makes sure you don't make extra errors. So it's handy to still keep the subscripts, I think. But remember, we're not doing anything complicated. This is still just z is equal to x minus mu over sigma. Except now x is a mean, the critical mean. Mu is the mean under the alternative distribution. And sigma is just sigma sub x bar. It's the standard deviation of the sampling distribution of sample means. So we have all these values. It's 15.98 minus 16 over a half, or a z-score for that particular value of negative 0.04. Right? That's what we found. We found on the z-scale what that corresponds to. So the problem is just the proportion of a unit normal distribution greater than negative 0.04. Again, negative 0.04 is less than 0, so we know the proportion has to be greater than 0.5. So let's actually go to our unit normal table. We're going to look for 0.04, and the proportion in body is 0.5160. The bigger proportion, again, we know it has to be greater than 0.5. And that's why coming up with these intuitive guesses, I think, helps save errors. Because once we got to this point, we knew we were looking for a value above a half. So the proportion in tail and proportion in body distinction is no longer really necessary. We know it has to be the larger one. All right, so we've actually answered this question. The proportion of z greater than negative 0.04 is 0.5160. That's also the same problem of the proportion of x greater than 15.98 is 0.5160. And if we go back to what we were doing, we've answered the question. The power is 0.5160. And remember why that is. That's the proportion of the samples we could get if the mean after treatment was set at 16. That's where it actually was. That's the proportion of the samples that would be greater than 15.98. And remember what 15.98 is. That's the x-bar critical. That's the value of the mean that's exactly the same as the critical z-score. The z-score that we would have to exceed so that we wouldn't think sampling error was the cause. Remember, we set this situation up as if the null was true. What sample means would lead us to reject chance as the only explanation for what was happening, and we came up with positive and negative 1.96. Anything we got above or below those two values wouldn't really convince us that sampling error alone was the cause. We would have to get an extra explanation. We'd have to multiply entities in that position. Something else was happening besides sampling error. So what we found was the proportion of the time we would get samples that would lead us to that decision, that sampling error alone wasn't the cause. And we found that the power in this case was 0.5160. If the mean after treatment is really 16, then only about 51.6% of the time would we get samples that would lead us to reject the null. The rest of the time, we would get samples that would be easily attributable to chance. That is the rest of the time, the rest of the distribution that's not shaded in blue there. Those are samples that could be attributable to chance. Even though, from this bird's eye view, we can see that the mean is 16 after treatment, those samples, to the researchers on the ground who are actually doing the research, those sample means are reasonably attributable to simply sampling error. So they're not going to get to say that sampling error wasn't a good explanation, because in fact, in those cases, it actually is a good explanation. Despite the fact that they're wrong, it's still a good explanation. It's a parsimonious explanation for why the difference was there. All right, so what we've done, again, is finding the critical values in terms of x units, forgetting completely about the distribution of z sub x bar if the null is true, forget all about that, and then really forget that you're doing anything complicated. Just do this as a normal z-score problem. Now think about this. The previous study, this one I described, would have cost at least $60,000 if they did it this way, which of course they didn't. So it's 100 subjects, $100 a month for 6 months. So the power of this study, if there was a 1 hour difference, was 0.516. So meaning that even if there was a 1 hour difference in Facebook usage and sigma was 5, the chance of detecting the result was only 51.6%. Is this experiment worth doing considering the 48.4% chance of finding nothing? Right? So even though there was a real difference, 48.4% of the time, researchers would have to say they found nothing. They didn't find evidence of anything. They got a sample that looked as though it was chance. So think about that. Was it worth doing with such a high risk of finding nothing? I don't think I need to give you much time. Hopefully you say no. One should always consider the power of an experiment before undertaking it. That is, we should always think about what the chance is that we could actually find a difference we're looking for. A 1 hour difference is just not that much in a population mean, right? Especially if sigma, the standard deviation in the population, is 5. That's not that big of a difference relative to how spread out people are in general. Right? So this study probably was not worth doing. Now, of course, they couldn't know before the fact what the true mean difference is. But in certain experimental situations, we have an idea. We have a guess of what it could be. So considering power is always very important. Now imagine instead that the sample or the population mean after treatment was 17. We're imagining that our treatment has actually a much bigger effect, twice as large of an effect on the average in the population. Now, before we actually calculate it, I want you to answer this, true or false. if the true population mean after treatment was 17 hours, power would be higher than if the true population mean after treatment was 16 hours, assuming everything else stays the same. So if we double the size of the effect in the population that we're trying to figure out power for, should power go up or should it go down? So true, it should be higher. False, it shouldn't be. Again, hopefully you answered true. The power should increase, because this is what we saw in class. If we have the distribution centered at 16 there, and I redraw things to have that distribution centered at 17, notice that most of the sample means we could get will be above 15.98. Said differently, most of the sample z sub x bars will be greater than 1.96. What that means is most of the time, people are getting sample means that can't be confused with chance. They can't be confused with a sampling error only explanation. Most of those sample means are so far away from 15 that they look as though there's a real effect. Because don't forget what the whole purpose of doing hypothesis testing is, to determine whether it's sampling error or whether sampling error isn't reasonable. So if the effect is really large, let's say 17 is the mean after treatment of the population, all those samples are trying to estimate 17. That's what they're centering towards. So most of those samples are going to land, even the most extreme ones on the left-hand side, most of them are landing in a region where it can't be confused with sampling error. Right? These samples, all of these ones up here, exceed our criterion for when we're going to say sampling error alone is not a good explanation. Now there still are a few samples you could get if the mean after treatment was 17. There's a few times, right, researchers are going to get sample means that are down here, where it looks as though sampling error could have been the explanation. But that's just not going to happen very often if the mean after treatment is actually 17. Most of the time, the sample means we get will be so far away from 15 that they couldn't possibly be confused with chance. They couldn't possibly be reasonably attributed to sampling error only as an explanation. All right, so what we're going to do is calculate power again. Right? So we know all we have to do is find the critical value in x units. We've already done that. Forget completely about the distribution of the null. We're actually not going to forget about it. I'm going to keep it up there, but notice that you can just forget about it. We're not going to use it. And step 3, forget that we're doing anything complicated. That's something you could always do. So just forget we're doing anything complicated, because we're really not. We're just z-scoring again. But what we have to do is figure out where that x bar critical is now relative to this new population mean. The mean under the alternative centered now at 17, not 16. And now notice it's going to be further out in the distribution. 15.98 minus 17 is a larger value, right? It's more negative, but it's a more extreme value than what we had before. So the z-score in that distribution of the alternative is negative 2.04. Specifically, what I'm saying is that 15.98, the x-bar critical, is 2.04 standard errors below 17. It's very far out in the tail of that distribution under the alternative hypothesis. And all that means is that most of the distribution is above 15.98, which we've already seen. We can see it in the diagram here. Most of the sample means we could possibly get if the population mean was centered at 17. Most of the sample means we can get are going to be above 15.98. So all we've done is found the z-score in a unit normal distribution that corresponds to how far out 15.98 is relative to 17. As all we've done is convert it to a z problem. Now we can go to our unit normal table. We're going to look for that z-value, 2.04, and we see the proportion in the body is 0.9793. Now remember what that is. That is now power. That's the proportion of the time, if we're actually taking a sample from a distribution centered at 17, that we would get a sample mean that would exceed 15.98. Or said differently, that's the proportion of the time, if we're taking a sample from a distribution centered at 17, that we would get a sample z sub x bar exceeding 1.96. Said yet another way, that's the proportion of the time we would get a sample that isn't going to be confused with chance as an explanation for why it's so extreme. That is only about 2.1% of the time will a researcher doing this experiment, if it's actually trying to detect a mean after treatment of 17, only about 2.1% of the time would that researcher get so unlucky to get a sample mean that could be confused with chance as an explanation for what's happening. That is, the mean is so far out, 17 is so much above 15 in this particular circumstance with 100 people in the sample, it's so far out that it's just really not going to happen often that a sample mean will be so low as to be confused with chance. Now, importantly, because the sample mean, or because the population mean is so far out, even if we get unlucky and we get a sample mean that's down here, at 16.5 or something like that, even those sample means will still not get confused by chance. The only sample means that get confused by chance are the one that lands between positive and negative 1.96 in this distribution. Those are the only sample means that could have reasonably be caused by chance based on our criterion. And because so much of this distribution is above that, it's just not going to happen much of the time. So we've increased the size of the effect here, and this actually has real relevance to some research. Let's say we're doing drug research, and we have a drug that we want to see if it actually affects pain relief. We don't know if it does or not, but we want to decide if it does. And let's say we know we can give a lot of this drug without hurting anybody. We know it's safe for people. We just don't know if it affects pain relief. If we had the choice, we would choose to give a huge amount of the drug and compare it to a placebo, rather than just a little bit. Because we want the effect that we're trying to detect to be really large, right? We want it to be as large as possible so that we can actually see and actually have a chance at detecting the real effect. So if you have the option of trying to detect a big effect or a small effect, of course you want to try to detect the big effect, because more likely is going to be that you can get a sample mean that won't get confused by chance. Right? More of the time you'll get a sample mean that's going to be far enough away from the mean under the null hypothesis that it won't be confused with a sampling error only situation. Right? If you have a coin that's biased and it's only biased in a tiny little bit, it comes up heads maybe 50.1% of the time. Most of the time when you flip the coin 100 times, you're going to get samples, right? Sample estimates of how many heads you have that look as though it could have just been sampling error. 52 heads, 58 heads, 51 heads, things like that. But if the coin is biased at 99 out of 100, that is, it's so weighted in a weird way that it comes up heads 99% of the time, then every time you flip the coin 100 times, you'll get a number of heads that can't reasonably be caused by chance. You'll get 98 heads, 99 heads, 94 heads. Some of the time you may get even 88 heads, but even 88 heads out of 100 can't be confused with sampling error, because you wouldn't expect that to happen if the null was true, if the coin wasn't biased. This is exactly the same situation here. If the mean after treatment is really far away from the mean before treatment, then most of the samples you get can't be confused with chance. Some of them can be, and in this case only about 2.1% of them, right? But most of them can't be confused with chance. That's what calculating power is all about. But notice we had to pick a mean for the treatment mean after treatment. We had to know what that was, right? And so this is something you can't often do in research, but it's at least something you can make a prediction about. We know the mean after treatment wasn't going to be 200 hours of use. We can reasonably say it wasn't. So if we did this study, we could have picked reasonable means after treatment and actually tested power to make sure we had enough subjects. Because one way you can always increase power is getting more subjects in your sample. That'll reduce the standard error. That is, these distributions will get more narrow. More of the time, your sample means will be close to whatever they're trying to estimate. So your critical value in terms of X units, that 15.98 here, would actually go towards 15, because more often than not, the sample means you would expect to get would be closer to 15. Also, the sample means coming from the blue distribution, under the mu treatment, most of them would be closer to 17. So if we increase sample size, the power we can drive up to almost 1, because we can make it a certain circumstance where it would never happen, almost never happen, that we would get a sample that's confused with chance as an explanation.